Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and in this lecture, we're going to be talking about local and global drivers of temperature. So we've been talking about energy, we've been talking about heat exchange. Now we're going to focus on kind of the expression of that, temperature, and what drives variations on a local scale to start, and then on a global scale. So first off, we're going to look at surface air temperatures, and a little bit of this is going to be review. Because we learned that temperature itself is just a measure of the average kinetic energy of randomly moving gas molecules, right? We looked at these GIFs here. The left is a GIF showing a colder air parcel. Notice how slowly those molecules are moving. The GIF on the right shows a warmer air parcel. Look how fast those particles are moving. They're more excited. We feel that expressed as temperature. So here's just a GIF of a thermometer, right? And how a thermometer works. Well, as these molecules are colliding with the thermometer, they're transferring that energy into the mercury on the inside. The mercury expands or contracts based on the temperature, and we see that expressed as where it is on the thermometer, right? Where that red line is extended to. We know we use units like Kelvin, degrees Celsius, or Fahrenheit to express temperature. Kelvin is our SI, or System International unit, that's necessary for many calculations. If we're thinking back to our lecture where we're looking at laws of thermodynamics and laws of radiation, we were looking at things like Wien's displacement law and the Stefan-Boltzmann law. Those both use Kelvin to calculate the different types of wavelengths that we're interested in. Surface air temperature is incredibly variable. Whether you are measuring it over asphalt or in a grassy field, underneath a tree that's shaded, there are so many different things that impact what that temperature could be. So we use a few things to kind of moderate and confirm that we're actually measuring ambient air temperature. So one of the tools we use is a Stevenson screen. We learned about that before. Placed at about 1.2 to 2 meters above the surface is where the actual gauge is. It's in the shade, and the shade is within the Stevenson box, or Stevenson screen here. And it's over natural ground cover. It's not over something like asphalt or the top of a building or something like that. We use other metrics to, and other equipment and instruments to measure temperature there. So here you can see it's just this white painted box with these side panels to allow air to get in there. It's shaded so that the actual instrument is not being affected by the sun. It's piping kind of air in and blowing it over the instrument so that it's getting an accurate reading of air temperature. We can also see here, it looks like they're trying to verify some of those temperatures. If you look in the back here, that and this here, if you can see my little squiggly lines there, the left side and the upper right, those are wind gauges. So there we're looking at anemometers. It's hard to see here, maybe a cup anemometer with a wind vane on the top to look at direction and wind speed. So now getting into the diurnal and temporal controls on patterns within surface air temperature. So surface air temperature is controlled largely by the radiant energy balance of the surface. Recall in our last few lectures where we were talking about incoming solar radiation or insolation, we learned how to calculate some of the things related to insolation for a given place at a given time of year. But we really only have net energy gained through insolation during the time when the sun is visible. So if we're looking at a diagram like this, which is showing the amount of incoming energy lost and gained, we see that on the bottom, that blue line with the blue area shaded and the red line with the red area shaded. And then that green line is showing our temperature throughout the day. So we're looking at temperature in time from midnight on the left to midnight on the right. So we see temperature here and radiant energy gained or lost. So what we're doing is kind of comparing when temperatures are the coldest or hottest compared to what energy is doing at the same time, whether we're losing energy or we're gaining energy. we can see a few different interesting relationships here. Uh, get down here. The first one that we can see is that these minimum and maximum times don't actually line up really well with when our uh, energy lost and energy gained is occurring. It's not happening at the exact same time. There's a lag time for when energy lost is kind of ending, I guess, if you will, starting to ramp back up into a net surplus of energy, and when the minimum temperature is, and then when we peak with our maximum energy gained, and when the maximum temperature is. So there's a lag time between these two different things here. Um, why is that interesting to note? Well, they don't line up with sunrise and sunset that you would think they would, or sunrise and solar noon and sunset. So actually, as the sun starts to rise, the Earth is roughly at its minimum point of long wave emitted energy, having been emitting this energy throughout the entire night, right? It's always taking in energy, it's always emitting energy to get that energy balance, but when it's not being heated by the sun during the daytime or during the nighttime, so when it's dark out, it's emitting, it's giving off that radiation in the form of long wave thermal infrared radiation. And it kind of gets to its minimum point just before sunrise. Then sunrise happens, right? And then we start to see sun coming above the horizon. That insolation is starting to get to a point where maybe it's still pretty horizontal, but it's starting to get up to a point where it's starting to strike the Earth again. When it finally spreads above the horizon and spreads those first faint rays of solar energy across the surface, there's finally some incoming radiation. However, for several minutes, the meager amount of incoming radiation is not sufficiently large enough to actually start warming the surface and counter the amount of long wave energy still being emitted. As a result, the surface temperature continues to drop even in the face of the newly risen sun. As Earth continues to heat up throughout the daytime, materials across the surface are getting warmer. And you can see that in kind of the peak here of when we hit our peak of absorbed solar radiation. However, it isn't until a little bit past noon, sometimes mid-afternoon, until the energy lost, which we feel is heat, is at its maximum point. So we're gaining that energy, right? We're warming the lower parts of the atmosphere. We're giving off that thermal energy from the Earth. And where the maximum temperature is, that dashed line where the green line peaks going down, and where the net long wave radiation is peaked, you can see that. Right between where I have sunset and that maximum temperature line, that's where we're seeing net long wave radiation at its maximum point. So that's when we're feeling the day is the hottest. This might not be till 3 o'clock in the afternoon, 4 o'clock in the afternoon, when temperatures are kind of sweltering. But it just kind of goes to show that just because we're seeing, we might have sunrise or sunset or solar noon, that doesn't necessarily correspond to the coldest or warmest temperatures of the day. And we can see those these relationships reflected in this real data set here from the Eau Claire Regional Airport, September 29th, 2012. We can see the sunrise with the coldest temperatures just after sunrise. We can see solar noon and the warmest temperature shortly thereafter. We see sunset and our temperature starting to drop off again much more rapidly. Now, on a sunny day, this is a pretty consistent relationship, right? This is easy to map out when there's nothing impeding insolation coming in, but that's not necessarily the case all the time. We have things like clouds, wind, humidity, all these things impact the amount of insolation absorbed by the Earth and given off. So on days with variable weather, like cloudy days, humid days, or windy days, we actually might see these relationships. And the greater reflection of insolation by cloud cover, greater absorption of insolation by water vapor, or the greater mixing of air masses by the wind, which gets to our next one here. Forced convection, or what we call mechanical turbulence. So we may recall hearing, I've been mentioning a couple times now, that pressure and the driver of wind across our planet is differential pressure. So air in high pressure zones is going to move towards air in low pressure zones due to what we call the pressure gradient force. We see that in that little GIF up in the top left of our image here. This exchange can lead to forced convection, which we also refer to as mechanical turbulence. Given that warm air rises into the atmosphere and cold air descends, we see here a little animation there. This forced convection is driven by mixing of air masses, which we're kind of seeing this kind of upwelling or upsweeping gusts there as warmer air is rising and mixing into colder air parcels above. And this mixing, as cold air descends and warm air rises, is really what drives what we call turbulence or forced convection. Now, if these systems were perfect, we would expect to see symmetrical peaks and valleys within our temperature across a given period of time. But instead, we see a considerable amount of noise on a real graph of temperature versus time, right? Well, these variations in pressure and wind across the surface impact the distribution of energy and drive differences in surface air temperatures. Here we're looking at a 1-month record from the 12th of March to the 13th of April, showing widespread variations in diurnal temperatures. So just based on temperature alone, we can interpret that there's probably substantial cloud cover right where above where this bar is here, because we're looking at ranges that didn't change that much. There might have been something insulating the air below the clouds or insulating the air near the surface, so that temperatures variations were much more muted than we see some other times. If we look over here, we likely had sunnier days, maybe with a warm front moving in, and likely, potentially, a lack of snow. Why do I say a lack of snow? Well, we're seeing these big shifts from time to time, and what we aren't seeing is, we're seeing, higher temperatures in general, so there's not as much reflecting insulation back. So here, perhaps the ground is starting to be exposed. We're absorbing more of that energy through the darker color of the ground below where the snow would have been previously. And maybe it's a clear sunny day. So we're seeing these variations where we wouldn't if there had been perhaps cloud cover. All right, now we're going to move into some local patterns and controls on surface air temperature. One of the easiest ones to understand is topography, right? Looking at the contouring and lay of the land, we can see certain things like cold air drainages here, right? Cold air is denser, so it's going to follow the contours of the landscape. We see that here reflected in this high mountain area, where notice where all the clouds are. And at that point, the air temperature and dew point, which we'll talk about here soon in the next set of lectures, talking about moisture and atmospheric stability, the dew point and temperature have reached one another. We have condensation and cloud formation. We have colder air that has been rushing down into this valley area. We see that reflected here as well. Notice where the fog is forming. The fog is forming in these low areas. It's not forming on top of these low hills. Now, temperature also has an impact on things like vegetation cover, which we'll talk about here in a little bit, has a big impact on temperature. So notice here, and we'll pretend that we're in, for example, the northern hemisphere. It's very likely that the slope on the left side of the image here is a south-facing slope, where the slope on the right side is a north-facing slope. Why do I say that? Well, one, you see a lot more barren vegetation cover on that left slope, what I'm interpreting as the south-facing slope, because the soil is going to be much less moist than the slopes on the north-facing slope. They're going to be a lot hotter, so they're not going to be as supportive of things like forests that you see on that north-facing slope there. And that in itself can have a huge moderating effect on temperature below the canopy of the trees. So in general, it's not getting as much insulation on the north side, and it's also going to be colder underneath the trees in general. We call that slope aspect is the big play, whether it's a north or south facing slope, depending on where you're at in the world, that is going to be impacting those temperatures. And we can see that here as well, just another example. As I alluded to, vegetation cover, it has a big effect on temperature. Aside from trees kind of acting like clouds, right? It can intercept, it can reflect, it can do things like block insolation, provide shade. It gives a slow loss of long wave electromagnetic radiation to space. And trees transpire a lot. They give off a lot of moisture, which can also uh, absorb that energy coming in. So forests and trees can really moderate temperatures. And think of how cool it is under a dense forest canopy in the summertime, even if it's really, really hot. If you're standing in this picture that we see here, if you're standing in this grassy area versus standing under that canopy in the back, it'd be a lot warmer in that grassy area than it would be within the canopy. Unless you're somewhere like this in the semi-arid to arid Southwest, for example. Here, the vegetation is substantially smaller, but you'll see congregation of bugs and animals and critters and all that kind of stuff underneath where the vegetation is, because even though it's small, it can provide some shade and can provide some temperature moderation, although much less than if you were in somewhere with developed forests and massive canopies like you're seeing in that top left image. Next up, we're going to dive into global drivers in surface air temperature. So here we are looking at two maps. This is the top map on the right is a January surface air temperature map, and the bottom left is a July surface air temperature map. What we see, these bars and lines that we're seeing, so the gradational color and the lines associated with it, we call those isotherms. And really they're showing where pressure is, or sorry, not pressure, where temperature is kind of contouring, the average temperature, for example. So each of those steps up by, it looks like 3 or so degrees Celsius. It kind of depends on where you're at. But if you look in the January one, notice where the thermal equator is, that line cutting right through the middle of the world. Well, it's dipping pretty far into the southern hemisphere. And that makes a lot of sense, doesn't it? Because we've talked about how in January, right after the December solstice, the subsolar point is directly over the Tropic of Capricorn, 23.5 degrees south latitude. So the warmer temperatures are going to be focused in the southern half of the world. Likewise, in July, that thermal equator jumps up to the northern portion, north of the equator, and follows kind of close to that 23.5 degrees north latitude. Again, because our subsolar point, where we're seeing the most incoming solar radiation or insolation, is north of the equator. And here we can see another example of this. There's a few things that we can see here. Some pretty extreme temperatures in inner Russia, for example, and in northern Canada, which is kind of surprising, right? You wouldn't expect that, but we'll talk about the effects of continentality here in a little bit. Along oceans, we see kind of cooler temperatures, or along big bodies of water. Another effect we'll talk about here soon. And then areas where you are very high up, elevation, plateau, those are typically cooler than lower areas. And again, we'll talk about that here in the next couple of slides, but this just kind of show an overview of the globe and average temperatures across our world. So the first control on global surface air temperature patterns that we're going to talk about is pretty simple. It's latitude. We saw this when we were looking at our net daily incoming solar radiation map in a few lectures ago. Temperature generally decreases with increasing latitude. Well, why is that? Well, insolation intensity generally decreases with increasing latitude. We learned this pretty extensively, right? It makes a lot of sense. When you have a higher incoming sun angle or solar angle there, you're going to have a more diffuse energy or amount of energy coming into any one given square meter, for example, as we've talked about. So that energy is not going to be as effective at warming the surface as it would be if you were somewhere where that sun angle is much higher. You're top down, you're straight above you, for example. Annual temperature ranges generally increase with increasing latitude as well. So the highs can be higher, the lows can be much lower. Why is that? Well, we're going to look at our solstices here just to give you an idea. So here we should recognize this kind of sketch out. We're looking at the equator, the Tropic of Cancer here, 45 degrees north latitude, right about where we live, and then 66.5 degrees north latitude, the Arctic Circle. So in the December solstice, obviously the subsolar point is down near the Tropic of Cancer or Capricorn, 23.5 degrees south latitude. So at the equator, 12 hours of daylight, 1,248 watts per meter squared of incoming solar radiation, 928 watts per meter squared and 10.5 hours of daylight, 499 watts per meter squared and 8.5 hours of daylight, 0 watts per meter squared and 0 hours of daylight, the land of the midnight sun. So we can see how in winter, for example, these times can vary pretty extensively from the equator all the way up to the North Pole. Now let's look at what it looks like in the June solstice. Equator, it's the same thing, 1,248 watts per meter squared, 12 hours of daylight. At 23.5 degrees north latitude, it's kind of our solar constant, right? Sun is coming directly overhead. The average net incoming solar radiation is 1,361 watts per meter squared, or 13.5 hours of daylight on the June solstice at that point. 45 degrees north, right about where we live, 1,266 watts per meter squared, 15.5 hours of daylight. And up in the Arctic Circle, 995 watts per meter squared, 24 hours of daylight. We go from 0 watts per meter squared of incoming solar radiation and 0 hours of daylight to 995 watts per meter squared and 24 hours of daylight. Likewise, we go from almost basically 500 watts per meter squared, 8.5 hours of daylight, to 1,266 watts per meter squared and 15.5 hours of daylight where we live. Think of how wildly different it is in the December solstice versus the June solstice here in Eau Claire, for example. So we look here, for example, if we were to look at Manaus in near the equator versus Dallas-Fort Worth, roughly 35 or so degrees north latitude, and Churchill, Manitoba, up near about 60 degrees north latitude. Let's just look at a couple of temperature graphs here. So these are our mean monthly temperatures in Manaus, virtually unchanging from January to December. It is right at about, we'll say 26, 27 degrees Celsius. Dallas-Fort Worth, a noticeable peak during the summer months, the warmer months of the year versus the colder months of the year. We go from about 7 degrees Celsius in January all the way up to about 30 degrees Celsius in July and August. And if we're up in Manitoba, we go from negative 27 degrees Celsius all the way up to about 11 to 12 degrees Celsius. Some pretty wild fluctuations in average temperature for a given month in a given year. To ask, in which month does temperature decrease most rapidly with increasing latitude? We'll take a second, just kind of look at these again. And it looks to be August, right? We see the sharpest drop off starting just after the high sun point during the year and really starting to drop off into mid to late summer as we move towards our fall and winter. And that's because our sun angle is changing rapidly at that point relative to where you are in the higher latitudes, going from, very high above you to almost gone, right? So you're seeing a rapid fluctuation in those, post-summer going into winter. Now, the same can be said, more or less, for winter going into summer. You see, again, those peaks are much peakier, if that makes sense. The next one, elevation. So temperature generally decreases with increasing elevation. And just as a quick aside, just so we're all clear, when I use the term elevation, I'm referring to a point on Earth's surface. Altitude refers to a point above Earth's surface. I've used both in the last number of lectures, so I just wanted to make sure to clarify that elevation means we are at a point on Earth's surface, we're feet on the ground. Altitude is if we're flying in a plane or there's a satellite in orbit, something like that. That's what we're talking about. Or the levels of the atmosphere. We used altitude when we were talking about the height of the troposphere, the mesosphere, the thermosphere, and all those. But we want to ask ourselves why. Well, on average, about 50% of the sunlight arriving at the top of the atmosphere passes through the atmosphere and is absorbed at the ground. About 20% is absorbed by gases in the air, 30% is reflected back into space. This warms the ground. The air in contact with the ground is warmer than the air just above it. As you get further and further and further away from that warm ground, the air is colder and colder. So this explains why temperature decreases with increasing altitude within our troposphere. That's why you can see snow-capped mountains there, but have a beautiful sunny day down in the valleys. If we look here, we've seen graphs like this before when we were looking at our atmospheric structure. In the troposphere, as you rise away from the surface of the Earth, you drop pretty rapidly in temperature. So we go from, we'll say on average, 18 or so degrees Celsius, all the way down to about negative 58 degrees Celsius. Then, once you get into the stratosphere, mesosphere, and thermosphere, there are other controls there. But while you're in the troposphere, where we live and where Earth's surface resides, that distance from the surface is the driver of the major controls on temperature. It's why you can see snow-capped mountains, right? The next big control is land-water thermal contrast. We've talked about water. We're going to really talk about water next week or in the next set of lectures, depending on when you're watching this. So near large bodies of water, surface air temperature is generally warmer in the winter, cooler in the summer, compared to areas without large bodies of water. That moderating effect on large water bodies on surface air temperature is what we call the maritime effect. The absence of that maritime effect is called the continental effect or continentality. Why is that the case? Well, water has a much higher specific heat than land. Specific heat is really just the quantity of energy or unit of mass of matter must gain or lose for its temperature to go up or down a degree. Water has a very high specific heat, which means it takes a lot of energy to warm it up, and it takes a lot of time for that energy to expend out of it. So it'll stay warmer. It'll take longer to warm up, but it'll stay warmer longer, and it's much more gradual curve versus peakiness that you see over, for example, a continent. It takes, for dry land, 850 kilojoules per kilogram of energy to warm it up, specific heat. Water, 4,200 kilojoules per kilogram. So you can see it's a drastically higher specific heat. Water can mix, land can't. That energy can be expended more efficiently through water because just like air as a fluid, water can mix. Warm water can rise, cold water can descend. And as it does so, it mixes and expends that energy, expends that heat. Water is also transparent. Land is opaque. Water can penetrate energy and sunlight can penetrate much further into water. It can't penetrate through land. So it's going to be, again, that energy is expended over a much larger area than it would be in the land, which is just heated at the very top, the part that the sun can hit. And then water can evaporate, land cannot. So we can have phase changes and latent heat exchanges between different phases of water. Again, expending energy or manipulating energy more efficiently than land. So if you were to look at Astoria, Oregon versus St. Cloud, Minnesota, here we can see Astoria, which is right along the Pacific coast. Here we can see St. Cloud, Minnesota. They are drastically different, even though that they're at almost the exact same latitude. Ocean currents are another really big controller on global surface air temperature patterns. There are warm and cold ocean currents based off of these big thermohaline circulation cycles that we will get into a little bit in a couple of weeks. It's not going to be the major focus. We're going to be doing a lot more interpretation at that point. But just know that because we have warm and cool currents, that can really drive temperatures. We have warm currents coming up the East Coast. We have cold currents, the California current, for example, coming down the West Coast. The Humboldt or Peru current, the Brazil current are also kind of West Coast, East Coast, colder and warmer. All of these have moderating effects on climate. For example, if you were looking at Victoria versus Iquique, a cold ocean current on the west coast, a warm ocean current on the east coast. There's Victoria and there's Iquique. So Victoria is on the west coast, Iquique is on the east, or sorry, Victoria is on the east coast, Iquique is on the west coast. So the cold current, look at that, temperatures hovering around 20 and below degrees Celsius, and Victoria hovering around 37 down to maybe 23 degrees Celsius. So those currents can have a pretty big effect on coastal cities and temperatures. Atmospheric circulation patterns are another major driver. Prevailing winds, or what we call prevailing advection. Here again, we can look at Iquique and St. Cloud. But let's throw in Halifax. So some of these big patterns that we can see in atmospheric circulation going across our world can have big effects on temperature. So here we saw these already. Let's go ahead and throw Halifax in there, right? So we go from -5 or so degrees Celsius all the way up to about 18 degrees Celsius. So there it's the effect of the moderating effect of warmer currents on the Atlantic coast and these big atmospheric circulation patterns as well. And just to kind of bring it all back, we can see kind of these big trends here in air temperature across our world. We saw this before, just to kind of put it in more perspective. Prevailing vertical motion can have a big control on air temperature patterns. Whether you are in an area where there is predominantly rising air or predominantly falling air, rising air, you have a lot of moisture falling out of the, we'll say falling out, but you have a lot of moisture and condensation and precipitation versus areas where you've got consistently descending air that's drying out. You'll have these arid deserts. And we'll talk about that again more in the atmospheric circulation section in a couple of weeks or a couple of modules here. But we can look at places like Little Rock and Abu Kamal. We see the drastic differences there based off of where these big vertical patterns are set up. Same with Verkhoyansk. You can see how drastic those differences are there. And we watch this GIF play out. This is average air temperature from 1971 to 2000. And we can just see basically how our Earth changes over a given year. We see where the warmer air is. We can notice as we go into May, that warmer area is rising northward, falling southward once you get to September through December. And basically, we're just kind of watching the Earth, I guess, wave or breathe, if you will. So feel free to rewind, mute me, and watch this a few different times. I think it's very interesting. There's so many different things you can glean from looking at something like this. But that's going to do it for this lecture. This was a chunkier set of lectures, a chunkier module. The next one will be a little bit less chunky. We're talking about moisture and atmospheric stability, but we still have a few things to get through. But that'll set us up for much more smoother sailing as the semester continues. So to recap, we talked about patterns and controls in surface air temperature, diurnal and temporal variations in air temperature, local patterns and controls, and global patterns and controls. So I hope you enjoyed that video. We will see you in the next one.